Yes.
No, because of isotopes.
Yeah, so they have some similarities, but they are different because of this thing called isotopes. We will get there in a minute, but I'm just going to change colors here and say that today we know that there are such things as isotopes. And isotopes are the same element with different masses. Right. We'll get to that, more discussion about isotopes in just a minute. The third thing that Dalton said, he took it a little bit past atoms and he talked about compounds. And so compounds are these substances that are composed of atoms in definite ratios. Of different elements. Compounds composed of atoms in definite ratios of different elements, right? And so our simplest favorite compound, water, right? What's the ratio of hydrogen to water in hydrogen to oxygen in water?
2 hydrogens.
2 to 1.
Yeah, absolutely. 2 hydrogens to 1 oxygen. And so, you know, this part of his theory still holds true, that for a given compound, that ratio is set, right? If we have H2O2, that's not water anymore. That's hydrogen peroxide, right? And so the third part of his atomic theory still holds. The last thing that he said, he talked a little bit about reactions, and he said that chemical reactions do not change the elements that are involved in it. Of course, this is the one everybody really hated, right? This is the one where all those alchemists were saying, but everybody says I can get gold. And he said, well, not really. And turns out he was right about that too. And so these are the 4 parts of Dalton's atomic theory. Most of them hold fairly true to this day, 200 years later, even with all the advances that we've made in chemistry. The only real change being the fact that all atoms of a single element are not necessarily identical. The other minor change that we've made since then is that these atoms, even though elements are composed of these small things called atoms, Dalton thought that atoms were the smallest piece of matter. Right? We know now that atoms are broken down into subatomic particles, but Dalton didn't know that. And so, you know, taking his theory, the full intent of his theory, he thought that atoms couldn't be broken down, but we know that they can be broken down into some subatomic particles. And we need to talk a little bit about what those subatomic particles are. Right. We have the electron, the proton, and the neutron. Hopefully you remember from a high school class or physics or something, that electrons have a negative charge. We'll often represent that by a negative either in parentheses or next to an ion or something. Protons have a positive charge. Again, we'll represent a plus in parentheses. And then neutrons have no charge. Which of these subatomic particles find their home in the nucleus?
Protons.
And
Protons
neutrons.
and neutrons, absolutely. So these two guys are in the nucleus, right? And this electron we think of as orbiting the nucleus. Okay. Another thing I want to point out here is that if we look at these masses, these are in grams, right? Grams are pretty small values. But if we look at protons and neutrons, they are pretty close to one another. To 3 digits, they are exactly the same, and then they change just a hair. If we look at electrons, their order of magnitude is smaller by a factor of 4, right? And so the mass of a proton, I'm going to abbreviate that with just a little p, is about the same as the mass of a neutron, a little n. But both of these are much, much bigger than the mass of an electron. Sometimes electrons are left as just E's, but often they're E's with a negative sign. I don't know why protons don't have a plus sign. But usually in our textbook especially, proton is P, neutron is N, electron is E with a little negative sign, right? And so most of the mass for any atom is in the protons and the neutrons. The electrons are about 2,000 times smaller in mass than protons and neutrons. Okay, so now that we know a little bit, at least, about subatomic particles, we're going to leave them behind a bit because that's for particle physicists. What we care about is how they, we care about the whole atom. We care about what they make up. We don't want to look at protons separately from the atom. And so we're going to talk about atomic number, the mass number, and then we'll talk a little bit about isotopes. The atomic number is represented by the capital Z, right? And the atomic number gives us the number of protons in the nucleus. Okay. When we look at a periodic table, the number of protons, the atomic number, is given up in the corner usually. So let me just draw maybe a little element box here. If I had carbon, you'd see a little 6 up in the corner, and that 6 is the atomic number. Right? The mass number for an element, for an atom, is the sum of the mass of the, it's the sum of the number of protons and neutrons. And so this is the number of protons plus the number of neutrons. Now, when we look at the periodic table, if we look at carbon, it's got 12.01 underneath it. Right? We can't have 0.01 of a proton or 0.01 of a neutron. And so the atomic mass and the mass number are not the same thing. Let me make sure that that's clear. So the mass number is not the atomic mass. Right? The mass number is just kind of a quick way for us to know how many subatomic particles are in the nucleus, right? It's kind of a quick and dirty way of thinking about the mass of a particular atom. Because we know that the number of protons is Z, we can also think about this mass number as being Z plus the number of neutrons. Right? When we talked about isotopes earlier, we talked about them as being atoms of the same element with a different mass. we're going to clarify that a little bit, because yes, they have different masses, but is it because they have a different number of protons or a different number of neutrons?
Neutrons.
Absolutely, a different number of neutrons. Right? And so if I took this carbon 12 just as an example, so carbon 12, well, just we'll get to isotopes in just a second. When we write our atomic symbol, the chemical symbol goes in the middle, right? So that's our C for carbon. We write the mass number, A, in the upper left. We write the atomic number, Z, in the lower left, right? And if there's a charge, I'm just going to put a dotted circle here. If there's a charge, we put it there, right? So again, this is mass number, not atomic mass, mass number. This is the atomic number, right? And here is the charge if it has one. Okay. And so when we have carbon with a mass number of 12, we say carbon 12. That's just sort of how we talk about it. And so that would be carbon 12, 6. He doesn't have a charge. And so if we were to add a neutron, he'd become carbon what?
13.
Yeah, absolutely. If we add a neutron, our mass number increases by 1. Does our atomic number change? No, I see lots of heads shaking, right? And so these two are isotopes. If I went to a mass of 13, but instead of adding a neutron, I added a proton. So my mass number went up, but also my number of protons went up. Is that still carbon? No.
No.
Does anybody have a periodic
No.
table in front of them? What do we have?
It becomes nitrogen.
Excellent. Yeah, we have nitrogen now, right? And so the atomic number tells us which element it is, right? So this is unique to each element. The atomic number, right, is unique to each element. The mass number is not, right? Carbon 13 and nitrogen 13, those both have a mass of 13, even though they're different elements. Okay. When I wrote the atomic symbol for carbon 12, I said it doesn't have a charge, right? If that's true, how many electrons would carbon 12 have? Go ahead and unmute yourself.
6.
6, absolutely. So we have to, if we have a neutral atom, an atom that's sort of in its natural state, then it has an equal number of protons and electrons, okay? All right, let's fill out a table and see if we know what we're talking about. All right. There are 12 things to fill out. I'm just going to go across my screen and call on you and see if you know what you're talking about. If not, it's fine. But if you know the answer, holler it out, right? All right, Matthew, you're first on my screen. How many protons?
11.
11 protons. Caroline, you're next. How many neutrons? You're muted. You can hold up a finger if you'd rather.
You have 9.
9
Right.
neutrons, absolutely. Sam, how about electrons? How many electrons do we have?
11.
11. Because we don't have a charge, it's the same as the number of protons. Okay. All right, Rosie, for the second line, how many protons?
11.
11. Taylor, how many neutrons do we have?
10. Or actually 11. Sorry.
11, yeah, good. Vanya, how many electrons do we have in the second row?
11.
11 again, yeah. And 11 all around for that guy. Okay, now notice in this third row, it doesn't give us the atomic number. But since it tells us what element it is, do we really need the atomic number as long as we have a periodic table? We don't, right? For those of you that don't have a periodic table pulled up, what should be, oh, it's green like my green screen. I can't show you any. Well, I need to print off a black and white periodic table. Pull up a periodic table, Griffin, and tell me how many protons are in oxygen 17.
Hold on, let me look.
Yeah.
Is that oxygen?
It is oxygen.
Could it be 15?
Not 15. So oxygen in the upper corner of that little square. What number do we have? Who's got it?
Isn't it just 8?
8. It is 8. Yep. And so that should be the number that's up in the upper corner when we look at a periodic table. So, Beard, if we have 8 protons, how many neutrons?
9.
9 neutrons. And we know that because we know our mass is 17. 17 minus 8 gives us 9. And then Lily, how many electrons do we have?
8.
8, absolutely. Okay. If I made this oxygen 2 minus, how many electrons would I have?
10.
10, right. So remember, adding negative charge means we're adding electrons, not taking them away, right? And so if it were 2 minus, I'm just going to put a slash here, that would be 10 electrons. Okay. Carbon 14. Michael, how many protons are in carbon 14? On the last slide, we said the atomic number of carbon.
6.
6 protons. That's our atomic number. May, if you're there, give me the number of neutrons.
Hold on. Let's see. Actually, don't know.
Okay. What's our, so when it's written like this, what's our mass number?
Would it be? Wait, wouldn't it be 6?
So 6 is.
Oh wait, no, 12.
protons.
Oh, 14.
14 is our mass.
Sorry.
No, that's fine. If 14 is our mass number and we have 6 protons, how many neutrons?
Oh, 8.
8, you betcha.
Okay.
Yep.
Perfect.
And then Abigail, if we have 6 protons, how many electrons?
Would it be 6 too?
It'd be 6. Absolutely, it would be. Right? And so you should be able to go back and forth from an atomic symbol or an isotope symbol, which is what we call these guys, to the number of subatomic particles and vice versa. Right? If I gave you the number of subatomic particles, you should be able to give me the number of, or give me the symbol. Okay. All right. When we look at a periodic table today, we see that it's broken into some, it looks kind of like a castle. We've got some high points, we've got some valleys. We have these funny 2 rows that are pulled out of the bottom here. You know, what does all this come from? Well, it's called the periodic table because certain physical properties repeat themselves and they show up periodically, right? And because of that, we call the rows in this table, we call the rows periods, okay? And so we have period 1, period 2, period 3, all the way down to period 7, right? And this image from our from an old textbook I had actually doesn't have the new elements. These elements have been discovered. They just didn't make it onto this periodic table. And so the next element to be discovered is the first element in period 8, right? Element 119. It hasn't been officially discovered yet, so we're still waiting. The properties, the physical properties that show this periodic behavior, the way the periodic table groups them is in columns, and so we call those columns groups, right? And we follow these group numbering, group 1, group 2, group 3, all the way over to group 17 and group 18, right? And so we just number them from left to right. You'll notice that there's a funny number letter system below it. We're not going to use that. That's used by more inorganic chemists. We're not going to pay much attention to that. We'll use just 1 to 18 all the way across. Right? Some of these groups I want you to know, and you may already know some of these names, right? The very first group here, group 1, who's got the name for that? Anybody remember? Anybody?
Isn't it the alkaline metals? Or...
Absolutely, the alkali metals. Let me erase my mark there. The alkali metals, and so alkali or alkaline, if you've heard that term, just means that it can be basic, and so these metals are very good at forming bases. Like if you think about acids and bases, they're very good at forming bases. That next group is the alkali earth metals. Again, they're good at forming bases, but most of these metals were discovered from the Earth's crust, and you know the naming of these kind of is a little old-fashioned. Right? If we go all the way over to the opposite end of the periodic table, group 18, helium, neon, argon, krypton, what do we call that set?
Noble gases.
The noble gases, absolutely. They're noble not because they think they're better than everybody else. Well, maybe they do. I don't know. They don't react very well with other elements, right? They're named that way because, you know, kings and queens of old didn't react with the peasants. So they are noble because they don't react with the rest of the peasants of the periodic table. And that group right next to them, group 17, fluorine, chlorine, bromine, iodine. Do we have a name for those?
Halogens.
Halogens.
Halogens, yeah.
The halogens?
That's it, absolutely. And so perhaps you have heard that term if you have like a halogen light bulbs or halogen lights in your vehicle or even at home. There are halogen light bulbs, and that just means that instead of what normally feels like a fluorescent light, you've got something with a little bit of chlorine in there, I think it is. Okay. Aside from that, we break the periodic table into a few other pieces. Right? And so all these tall groups, all these tall columns, we call the main group. And so that's these 2 plus these 6 are called the main group. Or those 8 are the main groups, I guess. So these are the main groups, right? those are the ones that by far most of the interactions that we're interested in take place with, right? We do see some interesting stuff here in this set of lower columns, these 10 here. You might know what these are called?
Transition metals.
Transition metals, yep. And then these down here, right? Really, these two belong in period 6 and period 7, but they pull them out so that our periodic table is not 2 sheets of paper wide, and it fits just on a single sheet of paper, right? That's the main reason they do that. These are called the inner transition metals. You may also see them called the lanthanides and the actinides, because lanthanum and actinium are the first elements there. I won't use those terms, but if you see it, don't let it confuse you. The inner transition metals. Last thing I'll say about the periodic table, and then we'll move on from this slide. In green, you can see it's classified as metals down here. And by far, most of the elements that we have are metallic elements. Right? So everything green is metallic. And so we usually think about this sort of stair step here, right, as the breaking point from it's going to be a metal if it's on the left, it's going to be a non-metal if it's on the right. So the blue ones, non-metals. And then the ones that I sort of squiggled over, those are metalloids. In some instances, they behave like metals. In some instances, they behave like non-metals. We don't have a very good classification for them one way or the other. Hydrogen can also sometimes be considered a metalloid. Every once in a while, you'll have hydrogen kind of behaving like a metal, but more often than not, he's a non-metal. Okay. Any questions about periodic table stuff? Hopefully a lot of this is familiar to you. Okay. So, molecules. When we talk about molecules, sort of our textbook definition of molecules is a set or an aggregate, right, when these things sort of get together. A set of atoms of one of the things that we require, right, just like H2O is always 2 H's and an O, it's also always the same structure. And so these two or more atoms, they have to be in a definite arrangement. 2 or more atoms in a definite arrangement. And those atoms are held together by chemical forces. Right? They're not held together by maybe static electricity. They're not held together by, you know, positive charge, negative charge, kind of electrostatics. They're held together by chemical bonding. Okay. Just for real quick here, since we've talked about water so much, when we think about water, it sort of has this shape, right? Those two hydrogen atoms are apart from each other by 104.5 degrees. You don't need to know this. I'm just sort of illustrating a point that water is always in the same arrangement. And those bonds that hold it together, we call them covalent bonds. And so these chemical forces, there's a couple types, right? Covalent bonding is what we call molecules bonding together. And that's when there is sharing of electrons between atoms. Okay. So when we talk about covalent bonding, we're talking about sharing electrons. Okay. A couple of terms that you might hear are diatomic and polyatomic. When we talk about our Greek prefixes, which we'll get to on Monday, di, what's that our prefix for? How many? 2. Excellent.
2.
Yep. And so these are only 2 atoms. And there's not a whole lot of diatomic molecules out there, but carbon monoxide, right? That's 1 carbon and 1 oxygen. That's an example of a diatomic molecule. Polyatomic, of course, is more than 2. But the reason that I bring this up is because with diatomic, there are some elements that behave as diatomic elements, right? They are molecules, but in nature, these 7 elements are found as diatomic molecules. They are hydrogen, so H2, right? It's always 2 of them. Oxygen, nitrogen, fluorine, chlorine, bromine, and iodine, or iodine, if you like to keep it consistent. Okay. And so those 7 elements are always diatomic when we see them in nature. Okay. If I had a periodic table, I'd show you, but nitrogen, oxygen, fluorine, chlorine, bromine, and iodine are all in the corner of the periodic table, right? They form kind of a number 7, but there's only 6 of those, right? So nitrogen is here, oxygen, fluorine, chlorine, bromine, and iodine. And so the 6 of those are there, but they form a number 7. That reminds you that hydrogen over here in the other corner is also diatomic. Right? There's also funny little mnemonics that maybe you picked up in high school. I don't remember them off the top of my head, but okay. So that's molecules. And then ions is the last thing we'll talk about today. And we will end it there. When we talk about fiddlesticks. When we talk about ions, these are either a molecule, an atom, and the only real way we form ions are by adding or losing electrons. And so these are molecular atoms with a net charge, and it can be positive or negative. Right? And if it's a positive charge, did we gain or lose electrons?
Lose.
Lose.
That's right. So here we've lost electrons, and if it's negative, we have gained electrons. Right? For positive ions, we have a special name for those. We call those cations. Right? This is not cation, like vacation. This is cation. Right? And if it's a negative ion, it's an anion. Right? So cations and anions. An easy way to remember that is the T in the cation looks like a plus sign. So you know that it's got to be positive. Right? Okay. Right. I think that's an excellent ending point for today. Any questions about this chapter 2 material? Again, these first couple chapters are probably fairly familiar to you. If you do have questions, of course, shoot me an email. Tutoring starts Sunday nights. You can head to the tutors and ask questions. Don't forget to keep up with your ALEKS. That stuff is due Tuesday at midnight. I'll remind you again on Monday, but I urge you not to wait till the last minute, especially if you have a ways to go. Okay. Any other questions? All right. I hope your first week has been good, if weird. Looking forward to the weekend, probably. Enjoy it, and I will see you all on Monday, all right?
Thank you.
Take care.
Thank
Thank you.
you.
Thank you.